Okay, so how is everyone today? Good? So today's what, the 30th? Just October is almost done.
Don't say that. Soon all the Halloween direct expiration will be 75% off.
Right? Exactly.
And think of the candy. The candy.
My children are looking forward to it. So is my children's dentist. Because he's a capitalist.
Aren't they all?
So, oh, I said that on camera.
Was that cynical? My bad.
It was really good. Just a flat delivery like they all are.
Yeah. Okay, so last time we were talking about quadratic functions. Yes? No. So I'm waiting for one of the graders had a let me know over the weekend that something unforeseen happened to them, and in the end I'm waiting on 3 exercises to be graded. And I debated with myself whether or not to post just what I have already, but then I was afraid that I'd get a flood of emails saying, well, what about, I'm sure that I did exercise whatever, and then I don't know. It's not ideal situation, but that's what it is. So I hope that this grader can finish his task sooner than later. So I'll get in contact with him, see him face to face tomorrow. Other questions? Okay, so last time we were talking about quadratic functions. Any questions about that? The main idea is that all quadratic functions can be obtained from the standard one by shifting it around or flipping it upside down and stretching it. And at any rate, the extremal point of a quadratic always occurs where? I agree, but there's a specific name that starts with V, the vertex. The extreme. See that I refer to that as the joke, but really it's more like the threat that I'll do that silly phrase unless someone remembers. Vertex. So the extremal point of a quadratic always occurs at the vertex, and for a given quadratic, how do you tell whether or not the extremal point will be a min or a max?
Negative or positive
A, right? The leading coefficient being negative, what does that indicate?
That square opens up down.
Oh, so negative means opens down, so
The vertex is high.
so the vertex is high. Okay, and the other way, vice versa. Good. Any questions about any of that? Just a brief review of last time. Okay, so now we're in section 5.2. And this is polynomial functions. Poly, yeah, there's a Y in there, sorry. Polynomial functions. To remind you, the polynomial functions, well, we know the sequence of power functions. So this is a row from that table of functions that we talked about previously. So we have first f of x is x to exponent 1, f of x is x to exponent 2, f of x is x to exponent 3, and f of x is x to exponent 4. So then they look like this when you plot them. Okay, so that one's just a straight line, slope 1 through the origin. This one is good old parabola. This one is cubic. And this one quartic. Okay, so all information that you already knew. Well, a polynomial function has to have the form like the following. So f of x is a n x to n plus plus a to x squared plus a1 x plus a0 with a n not 0. Okay, and the n's have to be greater than or equal to 0 and integer. Okay, so now what I mean by that is that this is some real number multiplied by x to n plus some real number multiplied by x with exponent n minus 1, one less, all the way down to some real number a2, x to exponent 2, a1, x to, what's the exponent for this x? 1, it's implied, 1, and then this is some real number. Okay, so for example, something like f of x is 13x to 14 minus 8x to 5 plus 4x minus 9. So that's an example of a polynomial. So what I want you to see, the reason why I wrote these first, is that these are power functions, that's their name, but we're going to, in some sense today, reimagine them as polynomial functions that only have one term. Okay, so like this is a polynomial, but it's just got one of these things added up, just one of these. Okay, and we're going to ask, well, what would happen if we took, say, this x cubed and added to it some x squareds and maybe some x's and things like that? What would happen if you did that? So in order to be able to make sense of all that, we need some names. So when you have an x to n plus plus a2 x squared plus a1 x plus a0 with an not 0, and with these exponents in descending order. What do I mean by that? Right. So like this exponent is 14, and then the next one moving to the right, that one's 5, and then that one's 1, and then this one is 0. So they're in descending order. Each one of these is called a term. So this whole thing is called a term. The reason why it's referred to as a term has to do with the study of languages. So this is called would be called a terminal. So term is short for terminal. These individual items, so this thing by itself, this is referred to as the coefficient. coefficient. This exponent is referred to as the degree. So using that terminology, terrible. Then this is a term here. What's its coefficient? -8. And then what's its degree? 5. Good. And then what's this one's coefficient? 13. And what's its degree? 14. What's this one's coefficient? 4. And its degree? 1. What's this one's coefficient? -9. And what's its degree? 0. Right. This is the one with degree 1. Degree 1. And this one is degree 0. Okay, now with the exponents in descending order, the one with the largest degree, is singled out for special importance. This one is called the leading term. And so could someone speculate what I could possibly mean if I say leading coefficient? Yeah, the coefficient of the leading term. Okay. Further, is that the degree of the leading term is the degree degree of the polynomial. So for example, with this polynomial, what's the degree of this polynomial? 14. Because that one is the leading term, and its degree is 14. Okay, so now just beware that I try not to play this game very much, but the online homework plays this game all the time. It'll say something like 4x minus 5x cubed plus 7, and it'll ask, what's the degree of this polynomial? Well, the answer is 3. But say I change this to that. So on this, a significant fraction of students will say that the degree of this polynomial is 2, because that's the degree of the term that's furthest to the left. Right, but they're not in descending order. Right? So the degree is the one with the biggest one. So the degree is 3. And what's the leading coefficient for this polynomial? -5. Okay, so don't be, don't be misled by this silly little thing. Okay, so what I want you to look at and consider is that for example, this one right here. What is, considering it to be a polynomial function, what is its degree? Two. And what's its leading coefficient? 1. And it has no other terms. Similarly, this one has degree 3, leading coefficient 1, and no lower degree terms, etc. So now what we're going to consider today is, what if we were to add a bunch of terms to this one and see what happens, add terms to this, see what happens, etc. So to that end, I'd like for you to consider this polynomial. F of x is x plus 1 multiplied by x minus 1. Okay, so I gave it to you. I gave it to you in factored form. So what's going to be the degree of this polynomial? It's kind of hard to say until you get used to it. 3. You got it. So if you were to multiply this out and collect like terms, then the highest degree term would be 3. Because eventually this x will multiply by that x will multiply by that x. And there's just 3 of them, so the highest degree you could possibly obtain is 3. Let's verify that that's true. So what I'll do is I'll commute these factors so that they look like this, so that I have these two factors side by side, and then I can look at them and say, oh, but those are conjugates, and it's easy to multiply conjugates. So this would be like this, and then I can distribute the x and get x cubed minus x. So what I want you to see is that this is just like, if it weren't for that term right there, that would be a function that you already know, right? In fact, it's drawn on the previous page. But effectively what I said is I'm going to subtract x and then see what happens. Okay, I'd like for you to look at this representation, this factored representation of the function. What could I plug in? What input could I provide so that the output would be 0? What do you think? How about for this specific factor right here? What could we plug in so provide as input an x so that the output f of x would be 0? How about 1, right? If we were to replace x with 1, then that would be 2, that would be 1, and this one would be 0. And then the product altogether would be 0. Okay, what could we, for this factor, could we plug in to make the whole thing 0? -1. And then if you were to just plug in 0, then that one would just be 0. So what I want you to observe is that if we were to plot this function, we know 3 different inputs that would force the output to be 0, -1, 0, and 1. So I'll plot them right here. So at -1, the output is 0. At 0, the output is 0. And at 1, the output is 0. Okay? Then, if you were to plot a whole bunch of points, then you would observe that it looks like this. So from this right point, you'd go up. And from this left point, you'd go down. So if you kind of squint your eyes, if I cover this up a little bit, you know, it might kind of look like the cubic from the previous page. If you kind of squint your eyes a little bit. And then what it does in between these points is it goes up a little bit, and then, you know, you've got to come back down so you can go through that one, and then it goes down a little bit, and you end up crossing that one, and then now you're down here and you've got to go back up to meet that one, and well, that's all that it does. So it does this much. So the way that we're going to conceptualize this today's lecture is we're going to split polynomial functions into these two bits. So specifically, we're going to refer to this as the local behavior. So everything in here is local, and everything outside is global. So what I want you to see, and the main idea, is that because if we were to delete all of the terms except the leading term, and just look at that one, then and we cover up the local behavior, then that's what it should look like. Okay, so let's write that down in a table. So this is the global behavior. So given a polynomial function with leading term a n x to n with a not 0, a n not 0 and n more than 0. So given a polynomial function like so, then a 2 by 2 table. So in this first column, we'll say that an is negative, and in this second column, an is positive. Then in the first row, we'll say that n is even, and in the second row, n is odd. Okay. So, let's imagine this one for a moment. So in the case that n is even, and in the case that the coefficient is positive. So to help you think of a specific example, I'd like for you to think of the specific example when n is 2, so that's an even number, and an is 1. So what will we have if an was 1 and n was 2? Yeah, it'd be exactly the parabola, the one that you know and love. It'd be exactly the parabola. So the global behavior here is going to be like the standard parabola. The right side's going to go up, the left side's going to go up. But then in between the global behavior, you can have some kind of wiggle that represents the local behavior. So right now I'm not interested in the local behavior, I'm only interested in the global behavior. Okay, similarly, how about for this one? How will this one be similar to that one but different? Now it's going to open down. Now it's going to open down. Now the right side goes down, the left side goes down. And then this is the global behavior on the left, the global behavior on the right. In between, you can have some kind of wiggle. But eventually, for this polynomial function, you go far enough to the right, then you just start going down forever. Okay. How will this one look? So what's a specific odd number? It's 3, right? So a specific one would be 3. So let's consider the case when n is 3 and an is 1. Well, that'd be exactly the cubic, right? That'd be exactly the cubic. So let's draw global behavior that looks like the cubic. So the right side goes up, the left side goes down, Okay, and then the local behavior in the middle can have some kind of interesting wiggle that we'll talk about later, but right now we're just talking about global behavior. Okay, then what will be this last one? Very good. Okay. Now, what I want you to take away from this is that, well, in the first place, let's consider the even cases. Because, in a sense, the degree being even means it's going to be like a parabola, in the sense that this one with the positive leading coefficient would hold water, and this one with the negative leading coefficient would mostly shed water, with the exception of the wiggles that are near the middle. Okay, and then these are like cubics. So now suppose that I cover this up. That is to say, I covered up the sign of the leading coefficient. How do you tell which one is which? So remember that the way this was is these were both the same sign of the leading coefficient, and then these were both the same. So what do these have in common? The right side. Right? So the fact that the right side is going up, that means that the leading coefficient is positive. And notice that what's true about these two. The right side's going down. So the fact that these are both up means that the leading coefficient is positive, and the fact that these are both down means that the leading coefficient is negative. So now, as a matter of terminology, the way that you write something like this is as follows. So what I'm about to write something there. I started. What I want to say is that as you for this one right here, as you go to the left, you start going up. So right here you can do up and down, but what I want to say is that if you go far enough to the left, then from that point on you only go up. So the way you say that technically is to say as x goes to negative infinity, y goes to positive infinity. For this particular one. So how do I finish this sentence? As x goes to positive infinity, what? Y goes to negative infinity. And then I could write similar things here. So for example, on this one, how about this one? As as x goes to positive infinity, what does y do for this one? Also to positive infinity. Okay. So any question about this? Okay. So how about, for example, here's a plot. Something like that. And then I say, okay, as x goes to the left, blank, as x goes to the right, blank. And then the degree Is it even or odd? And the leading coefficient, is it negative or positive? Okay. So how about this one? Correct. So this is just mathematician speak for as you go to the left, really far to the left. As you go really far to the left, that is to say, you get past all this wiggle business, eventually you go down. So y goes to negative infinity. Okay, how about this one? Same, right? So y goes to negative infinity. Okay. Is the degree even or odd? Even. It's got to be even. So why even? Because they're both going down. Suppose that I didn't give you a picture. Would you still be able to conclude that it's even? Why? That is to say, suppose I gave you this. Right, because both of these are the same. Because both of these are the same, that's enough to conclude that it's even. Okay, then suppose that you didn't have that. Then is the leading from the picture, is the leading coefficient negative or positive? It's negative. How can you tell from the picture that the leading coefficient is negative? Well, that's two things. Then they're mixed. So I want just the only reason. I mean, I agree with you. It's right, but you gave me two reasons, and I just want the one reason why the leading coefficient is negative. Because, for example, if I was to take this drawing and take this left arm and then twist it up, it would still have a negative leading coefficient. And then it wouldn't hold water. Because the right side goes down. Very good. Any question about this one? I said negative. I said negative.
Wait a minute.
I was so careful to do it, and then. Sorry. Okay, so what I want you to see is that these, as far as the global behavior is concerned, this picture, these two lines, they each tell you the same thing. Right? I could give you just one of these. I could give you just the picture, and you could tell me this and then this. I could give you just this, and then you could say, draw me a picture, and also the other thing. So let's do that. Suppose that what I give you is this. I give you an axis and say, okay, as x goes to negative infinity blank, as x goes to positive infinity blank, and then suppose I say that the degree is odd, and furthermore that the leading coefficient is, say, positive. And then I want you to tell me these two, and also supply a picture that does that. Okay. So, what's the very first thing that we can conclude? Like the smallest possible byte. The right side's going up. Right side's going up because the leading coefficient is positive. Okay. Now, that's using just this. Okay, then now, the combination of these two tells us what? So taking these two together tells us how to get this one. It's going to have to be going the opposite way because odd polynomials have opposite behavior left and right. Also, did you notice that odd starts with O and opposite starts with O? I'm just saying. Maybe it's just meant to be. So then, finally, some picture that does this. Okay, so then, as a result, going to the left, we need to be going down. So something like this, say. And then going to the right, we need to be going up. So something like this. So it's got to look like this eventually. And then now my job is to draw some kind of wiggle in between. Terrific. Any question about this? Okay, so the global behavior is pretty straightforward. Now we need to get to this wiggle, local behavior. So specifically, we're going to tackle it kind of, in the first place, we're going to make note of this. So globally, this polynomial, because it has because it's of odd degree and positive leading coefficient, it had to eventually go up to the right and had to eventually go down to the left. But it had to go through these 3 points, and that kind of forces it to snake its way through those points, and that's the first place we're going to look. So have a look at this example. And from that example, I'm going to make a quite similar example. So for example, how about f of x is x plus 1, x minus 1. So if I were to stop writing now, it would be exactly the same example. But I'm going to make it just slightly different. I'm going to take this x and make it squared. So the only difference there is that square there. So again, multiplying this out and collecting like terms, I'll move the x squared to the front and then multiply out those conjugates to get this, and then distribute the x squared to get x to 4 minus x squared f of x. So what's the degree of this polynomial? 4, and what's its leading coefficient? 1, and in particular that's an even degree and a positive leading coefficient, so you know it's going to end up looking like this globally. But this subtracting the square causes it to have a bit of wiggle in the local region. So again, we know 3 points. We know that it's got to go through -1 and 0 here, and also +1. So it's got to go through those. Furthermore, from this point going to the right, what has to happen? Has to go up. And then from this point going to the left, what has to happen? Got to go up. It's got to look like this so that because it's an even degree polynomial. So now what we have to do is we have to wiggle through these points. Got to wiggle through them. And what I want you to think about for a moment, without me drawing it, is how could you possibly wiggle? How could you get the red to touch all three of these points and to be smooth and not, never get pointy, because polynomials never get pointy? We could draw down and then up and then try to come down smoothly, do something like that. So what I want you to see is that for these 3 points, we have to cross 2 of them. We have to cross the axis. Well, we could bounce off all of them, right? We could say, like, bounce off of that one, bounce off of that one, bounce off of that one. Okay? Or we could cross this one, and then if we cross that one, then we'd have to bounce off the last one. So can you see that you can't cross the axis every time? So let me be clear. If the picture looks like this, so if we cross that one and cross that one, then we have to, in a sense, bounce off of that one. We can come down and touch it, but we can't cross again because then we'd be on the wrong side. So which ones are going to cross and which ones are going to bounce is the question I want to consider. Well, the answer to the question is it's going to be this way. It's going to be that we'll cross the first one, bounce off the second one, and then cross the last one. But why will it look like this? Why are we going to bounce off the one in the middle? And why are we going to cross the 2 on the sides? It has to do with the formula. Can anyone see it? I'm sorry? It's not going to be this part. Well, I mean, it's not most clearly visible from this part. It's most clearly visible from this part. So what I want you to see is that for this factor, for this x, what is its exponent? 2. And then now I'm covering this up. But whatever I'm covering up is in parentheses, and what's the implied exponent for it? 1. And what's the implied exponent for this one? 1. So that's what these two have in common. That's why these two are crossing. And this one is 2. That's why this one is bouncing. Okay. So these 3 factors that's why we have these 3 zeros. These 3 zeros. And now we can say that remark is that suppose a polynomial's factorization factorization includes x minus c to exponent k. where k is some integer that's greater than 0. Well, and there's going to be two possibilities. In either case, considering like this one, for example, what do you need to plug in for this factor to be 0? X is 1. And what do you need to plug into this factor for it to be 0? Negative 1. And what do you need to plug into that factor for it to be 0? 0, right? What do you need to plug into this one so that it will be 0? C. So we're definitely going to have a crossing, a 0 at C, in either case. But if you look closely at them with a microscope, some of them will look like crossing, that is to say you end up crossing the axis, and some of them will end up looking like this, like you're bouncing off the axis. So here we cross. Here we bounce. And what's the distinction between these? Under what circumstance will you cross? And under what circumstance will you bounce? Has to do with K. Okay, so I agree that if K is 1, you'll do this. And if K is 2, you'll do something that looks like this. But what if K is 3? You'll do something like this one. Ah, but what if K is 4? Now you do something like this one. So what's the rule? Very good. So in this case, this is K is odd, and this is the case what the even case looks like. Okay, and we'll continue this discussion of local behavior next time.